Hi, hello, welcome to Meki Teki. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers for their continuous support and encouragement of creating these kinds of technical videos. And today's topic of interest is linear programming problem. This linear programming problem, it is an optimization problem. We can simply say LPP. So LPP, we can say LPP. It is an optimization problem. It is done for making an optimization. What does mean by optimization in an industrial engineering? We can say maximize the profit, minimize the cost, and minimize the resources. With the minimum amount of resources, how much maximum profit we can draw on, that is the model, that is a problematic model which is created by using this LPP, linear programming problem. Here, this LPP is designed by Dangxing George. Dangxing George was formulated and found out the LPP program during the Second World War period. So, this LPP will give a greater success. The live example is the Second World War. So, this content and this topic has been formulated over there. So, this is 100% it is a mathematical technique. So, max plays a vital role in LPP program. LPP, okay? So, it is a mathematical technique and it is an optimum allocation of resources is the main function of the formulation of LPP. With the minimum resources, how much maximum profit we can draw from the resources. That is the theme, that is the agenda of the LPP. Okay, with this information, I would like to give a more detail about the content. Here, as I said earlier, it is designed by Dangzhang George. The formulation of LPP, the formulation is a first of all it is a mathematical technique. So it is drawn in the first quadrant. So LPP, linear programming, we know that we have a four quadrants. So this is first, second, third, and fourth. This LPP is always in the first quadrant. It won't go to the third or second or fourth quadrant. It goes only in first quadrant only. So first quadrant, the linear relationship between the two functions, we can say two objective functions we can give as a linear programming problem. It is giving a very linear relationship between the two constraints. So without having any linear relationship, we can't do. If there is any inequalities, we can convert. The first step we can have to convert the inequalities into equalities. Then after that, we have to solve by using LPP technique. So it is a 100% mathematical technique, and here it is an optimization technique used to solve the problems that are having linear in nature, and optimum allocation of resources is the main function of linear programming problems. The objective functions we can have in LPP, we have a two things. One is objective functions and another one is a constraints. Here, the objective functions is defined by the company or defined by the firm or defined by the organization. So it is defined. defined by a company. If I say, if I am having a five machines, five CNC machines, with this five CNC machines is my resources. So with the optimum utilization of the resources, so without idling time, we can optimize the use of resources. And if I can able to make a maximum profit about this. So this is the function, this is the objective function defined by any organization which is using LPP model. So the main function is to maximize the profit. So any organization have to maximize the profit, and I have to minimize the cost cost associated with the product, minimize the cost associated with the product, as well as minimize the resources. So that is the thing. And constraints are the conditions or restrictions on the resources available. So with the restriction of the resources available, that is called as a constraint. As I said earlier, if I am having five CNC machines, I have restricted that my shop floor is capable of these five machines only. I can't move for the next shop floor, or I can't move for the alterations, or if I can't move to the adding in another machine. So like that, I have a constraints, only five machines is the constraints, five machines, five mins. So that is my constraint. So like that, so it is the restriction or the condition on the resources available. So that is called as a constraints. So generally constraints are in inequality in nature, so that is called inequality constraint. And here I have given a mathematical relationship between the constraints. So a11 a1 plus a11x plus a12x, like goes on, it is less than or equal to b1 or greater than or equal to c1, like that we have given. So an equations with inequality constraints. We have to note one thing: all variables should be in linear and non-negative in nature. Linear and non-negative in nature. uh, Therefore, we have to use a basic variable or a decision variable or a choice variable in order to found the negative variables or negative variables converted into non-negative, or inequalities converted into equalities, like that we have to do. So here an important thing, a decision variables are coming to picture. So the decision variables are the physical quantities whose numerical value indicates the solution of LPP. So that is the basic variable and a non-negative basic variable, and also it is non-negative variable. If I can say, so this is the decision variables. So this is the decision variables. So this is the inequalities. It is not equal. This is inequalities. So these are all the constraints. Okay. I hope that you have understand. Okay. Next, I will go move on the assumptions of LPP. And one thing I have to be clear, this LPP is a graphical method. First of all, it is a mathematical technique. The mathematical technique used by means of a graph. So it is a graphical method of uh, finding the better solution. So it is a graphical method. You have to notice this, since it is a mathematical technique, but it is solved by means of a graph. The assumptions of LPP is the certainties, all objective and constraint coefficients of LPP models are deterministic, that is fixed. All the objective function, decision variable, constraints all are fixed, like that. So like the equation 3x plus 2y. So here the decision variable is fixed, the objective function is fixed, and the constraint is also fixed. Either it is equal to 0 or greater than or equal to some x, some a or b, we can say like that. Okay, so it is a graphical method. In the graphical method we have a different kinds of a constraints. The one is redundant constraint. So here the redundant constraint is been like this. It have been illustrated in the figure. If any constraint does not affect the feasible region or solution space, then the constraint is said to be an redundant constraint. Redundant constraint is not an optimum constraint. You have to know this. Redundant constraint is not an optimum constraint. If I have a two constraints in x and y axis, I have found out an feasible region of this. If any of the condition, if any of the other conditions, if it may draw on the condition line like this, so this region is called as an, so this region is called as an redundant constraint. It is not at all needed because we have already fixed the feasible region. So this redundant region will not at all affect the feasible region. So that is called as a redundant constraint. Next one is a binding constraint. What is the binding constraint means? If I am having a feasible region over here and whatever the another solution or another iteration is happen, it also come like this, the same line, like the same line. It is also lies in the feasible region alone. So that type of constraint is called as a binding constraint. Here right hand side is equal to left hand side, like that. If you can see here, if x and y satisfies RHS, then if you have an equation 5x plus 6, 5x1 plus 6x2 is equal to 22, say x is equal to 2 and y and x2 is equal to 2. If you substitute here, 5 into 2 it is 10 plus 6 into 2 it is 12, which is equal to 22. Therefore the right hand side and the left hand side and the right hand side are equal. So these constraint is called as an binding constraints. So here we have a properties of LPP, properties or assumptions we can say. Certainties is all objective and constraint coefficient of LPP model are deterministic. As I said earlier, the objective function, that is coefficient should not vary with time. The coefficient should not vary with time. The objective functions, that is maximizing the profit, it won't change with the time. And the optimum use of resources, it won't change with the time. So like this is an fixed condition. This objective function, it is not a transient phenomena. Transient means it is not a short term. Okay, it is not a short term. And optimalities are calculated by means of a decision variables and optimize objective functions, that is called optimality. And the proportionality is the condition where x1 and x2 are directly proportional to the value of variables. If the constraints increased, the proportionality is also increased. If the value of the variable increased, then the constraint is also increased. That is called as a proportionality. Here we have a proportionality relation too. Okay. Next is the additivity. Additivity means adding of resources. So the adding of resources, the product X requires 4 hours in machine A and 5 hours in machine B. Let we say we have an 1 hour of delay period. Therefore, in order to overcome this 1 hour delay period, we can add some machine or we can add some activity. So that is the assumption. Next is the continuity and dividability. So it is a positive fraction values. So continuity and divisibility is the positive fraction values like 1 by 4 or 1 by 2. The decision variables is continuous permitted and non-negative values should satisfy the condition. The next assumption is fitness. The values and constraints are finite in number. So the values and constraints are having a definite numerical number. So that is our assumption. Next is an important thing, that is formulation steps. The problem formulation steps. We have a formulation steps like identifying the decision variables, writing an objective function, writing an constraint, writing non-negative restrictions, and objective functions and constraints are linear. So these are all the uh, important problem formulation steps we have to follow. So here you have to notice this. So the objective function and constraint are linear in nature. This we have to ensure first. Okay, then only we have to continue the next methods. Okay, so here we have a types of solutions. We have a types of solutions like, as I say earlier, we have a graphical method. We have a graphical method. So it is for only two decision variables and as many as constraints. So two decision variables and many constraints. So that is the graphical method. We have yet another method called a simplex method. Simplex method. So simplex method, it is for more than two variables. More than two variables. So for that condition we have used this simplex method. Here we have a two phase and big M. Big M. So big M method. So like that we have a different types of solutions. And next one is the dual simplex. So dual simplex method, we have a many variables as well as many constraints. Many. So many variables and many constraints. And also we have a special type, that is transportation problem. Transportation and assignment. So these are all also in the form of the special forms of LPP. So the transportation problem, assignment problem, the transportation is the how we have to deliver the goods or finished goods to the marketing place. Like that we have to calculate the transportation problem. In assignment problem, the which machine is assigned in which part, like that we have to uh, develop a problem, develop a mathematical solution as a special form of LPP. So here we have a types of solution. After all the types we can solve, the solution are in some of the conditions. One is we have a either maximum or minimum. We have only two types, maximum or minimum. In maximum or minimum, whether it is feasible or infeasible. Like that, here also feasible and infeasible. So here we have an feasible region. If it is the feasible, whether it is in bounded or unbounded. And infeasible means there is no solution for anything. Either it is a maximization problem or minimization problem. If the condition is infeasible, then it doesn't have any solution. If it is a feasible, then we have a either it is a bounded one or unbounded one. If we have a bounded means there is a unique and multiple solutions. Whether it is an unbounded means that is infinite solution, like in maximization problem. In minimization problem, if it is bounded, it is having unique and multiple solutions. If it is unbounded, it is having a unique solution. Like that we have given different types of solutions available in the LPP problem. Here the feasibility means, what is meant by feasible solution? It satisfies all constraint, it satisfies non-negative conditions. So like that is called as a feasible solution. Or infeasible solution means it is unable to satisfy all constraints. In final optimum table, the artificial variables remains in the table. So that is called infeasible one. And sometimes a set of constraints does not form a feasible region at all due to the inconsistency in constraint. So this is the infeasible region. So there is no bounded solutions. There is no solution for this. So there is no feasible solution. If a constraint like this, it is having a bounded solution value of here, it is have a solution value of here. There is no linear relationship between these two constraints. We cannot calculate the solution at all. Or if it is having a multiple solution, that is the constraint lines are parallel to the objective function. So this is the objective function. If I am having a many number of solutions which is parallel to the optimum solution, so that is called as an multiple solution. Next, it is an optimum solution. Optimum solution is which satisfies the objective function, and if any objective function will have a multiple constraint and multiple solutions, the joining points or cornering points, the cornering points joining a polygon, it is called as an optimum solution range. So this region is called optimum solution region. Always the optimum solution region are in some type of a polygon. Okay, so the corner points from the solution of the polygons is the optimum solution. It is unique and finite solution. It produces an unique and finite solution. The optimum value occurs at an extreme point or vertexes of the feasible region. So that is the optimum solution. Next is the non uh, generative function, non-degenerative function. That is, none of the basic variables are zero. Degenerate function is one or more basic variables are zero. That is called degenerative. Non-degenerative is none of the basic variable are zero. Next is an alternate. Alternative solution means it is having more than one solution. We can use an alternate solution. It is having a multiple solutions. If the first solution is not feasible, we can go with the second solution. Like that, if non-basic variables are zero and final optimum table is called as an infinite or alternative or having multiple solutions. If there is no solution, not possible to find a feasible solution. If there is a no solution, there is no solution, we cannot find the solution. Okay, no solution or infeasible solution, both are same. Infeasible solution, it is no solution. Okay, unable to satisfy all the constraints, unable to satisfy all the constraints. The final optimum table, the artificial variable remains in the table, that is called infeasible solutions. If there is some variables we cannot get a linear relationship, then we cannot find the solution at all. So it is having no solution. Unbounded solution is there is no boundary, there is no polygon can be found. So it can constrain the it can cut the objective function, the constraints are solved, but it won't form any of the polygon. Feasible but not form the closed polygon, so that is called unbounded solution. So the greatest value of objective function occurs at infinite or common feasible solution not bounded with the constraints. This is called as an unbounded solution. Next, I have to give a detail about the variables. We have a in LPP we have a three types of variables available. One is a stack variable, surplus variable, and artificial variables. In stack variable, it is having non-negative and less than or equal to variables. Like that, it is called as a stack variables. If it is a surplus variable, the minus minus the variable. Variables are in the minus in the form. Negative functions, negative variables are there. Greater than or equal to symbol is used. In artificial variables, constraints are equal. Constraint equal. Constraints are equal. So it is used in bigger method. So here with this, I have closed the session today of LPP. In LPP, whatever I have know, I have delivered to you. For the better understanding, you can see some of the uh, operational research papers or books for the betterment of understanding about the linear programming problem. So it is very very interesting one. So as whatever the knowledge I have know, I have delivered to you. So I hope you have all understand this. If you have any doubts, please let me know in the comment section. I will put another video for your better understanding. So until bye bye from Santosh. Thank you.